In this lecture, we are going to look at organometallic compound. So the question is, what are organometallic compounds? Now, organometallic compounds are compounds that have a carbon to metal bond. So any compound that have this carbon to metal bond is an organometallic compound. Now note that compounds like sodium ethoxide. Now what is the structure of sodium? Let's say sodium ethoxide. This is sodium ethoxide is CO3, CH3, ONA. Now compounds like sodium ethoxide are not organometallic. Do you know why? Because the sodium, which is the metal, is not directly bonded to the carbon. Now if you want to write the structure of sodium ethoxide, it's something like this. You have carbon, this hydrogen, this hydrogen, this hydrogen, and then you have this oxygen, which is this oxygen, and then this sodium. So you see that in compounds like sodium ethoxide, the sodium, which is the metal, is attached to the oxygen and not to the carbon. So this class of compounds are not organometallic compounds. Are you getting it now? So they are not organometallic. Not. Okay? So organometallic compounds are compounds that have a carbon to metal bond. Okay? And examples of the organometallic compounds that we are going to treat are, we have the Grignard reagents. Now the Grignard reagents are called organomagnesium compound. Okay, organomagnesium compound that were determined by Victor Grignard. Then organolithium compounds, the ones that have lithium as the metal. And then we have organocuprate reagents, the ones that have copper as the reagent, as the metal rather, the one that has copper as the metal. Then we have organozinc reagents, the one that has zinc as the metal that is attached to the carbonyl or to the carbon. Are we getting it now? So that is for organometallic compounds. Now, examples of organometallic compounds are, we have something like, if you have something like this, CH3, then MgBr. Now this compound is called an organomagnesium or the Grignard reagent. This is what is called the organomagnesium or the Grignard reagent. Are you getting it now? Organomagnesium reagent or the Grignard reagent. Okay, you call it the way it is. This is what methyl. So you first of all call the methyl, and then this is what magnesium. So you say methyl magnesium bromide. That is the name of this compound. Methyl magnesium bromide. Methyl and the magnesium are together, then bromine. You may separate them. Okay, methyl magnesium bromide. Is that understood? So if I should give you another compound like, let's say CH3 CH2 MgI, and I ask you what is the name of this compound, what would you say? Now this is ethyl, right? So you say this is ethyl. I told you that you write the alkyl group and the magnesium together. So this is ethyl magnesium, and then the halogen, which is what? Iodide, separately. So this ethyl magnesium iodide. So we can say indirectly or invariably that the organometallic reagent, they have the general formula of, the organomagnesium reagent or the Grignard reagent, they have the general formula of ROMGX, where RO is the alkyl group, okay, where RO is the alkyl group, alkyl. Of course, you know what Mg is, magnesium, and then X is the halogen, which can be chlorine, bromine, or iodine. Fluorine is very reactive, so in most cases, it's not usually used. we have chlorine, bromine, or iodine. Now, our focus in this lecture would be mostly on organomagnesium reagents, which are the Grignard reagent, which we said were discovered by Victor Grignard, of which he received a Nobel Prize for his contribution to chemistry. Now, these Grignard reagents, normally, I said they have the general formula of ROMGX, and I've already shown to you how they are actually named. For instance, if I have, let's say, this compound given to me, and I'm asked to name it or to determine if it is an organometallic reagent. Now, look at the compound I'm going to give. This. Then you have something like magnesium chloride. Now, how many carbons are here? This is 1, 2, 3. Now, this one's telling you that this compound has 3 carbons, which is propyl. Then you call the magnesium, name it, propyl magnesium chloride. Propyl magnesium chloride. This is an organometallic reagent, okay? So, and this one type of the various types of organometallic reagent that we have, we say these are Grignard reagents. Now, organometallic chemistry is a very broad class of chemistry because they serve as synthetic tools for actually synthesizing various types of alcohol and other compounds. Are we getting it? It's a very broad chemistry. So we are not really going to dive too deep into it. We're just going to scratch the surface of the organometallic compounds, and particularly the one we are going to take cognizance of is the Grignard reagent, which we are already doing that. Now let's look at the organolithium reagents. Let me just give a brief overview of the organolithium reagent. Now, organolithium reagents are reagents that contains a carbon to lithium bond. Okay, for instance, when you have CH3, this is this. You call it, now we say it contains a carbon to lithium bond. We call them the alkyl lithium. Okay, alkyl lithium. For instance, this you call it methyl lithium. Okay, methyl lithium. Take note that this L is with this alkyl. We call this the methyl lithium. Okay, this is an alkyl lithium. So that is the name of the organometallic, the organolithium reagent. Now, another thing that you must note is because of the electronegativity. Now, let's compare organomagnesium and organolithium. This is Cli, and this is what? Cmg. Now, the electronegativity difference here is very high. And what makes this compound very useful is the ability of carbon to withdraw electrons from lithium, making the carbon to be partially negative and then the lithium to be partially positive. So that this partially negative carbon can act as a nucleophile to attack the carbonyl groups or other groups that it undergoes reaction with. So the more electronegative carbon is, the higher the reactivity. So you can see that between lithium and magnesium, which one do you think is more electronegative? Magnesium is, of course, more electronegative than lithium. Lithium is more electropositive than magnesium. So you see that because magnesium is more electronegative than lithium, it will make the carbon here to be more electronegative. That is, the carbon in the carbon lithium bond here will be more electronegative than the carbon in the what? Than the carbon in the carbon magnesium bond. Now, let me try and explain this. Let us say the electronegativity of carbon here is 4. And then let's say that of lithium is 1. This is an illustration I'm just trying to make. Now, if you check the difference in the electronegativity here, what is it? 3. So it means that the carbon is more powerful than the lithium, and hence carbon will be more negative as compared to lithium, right? Now, how about this? Let's say the electronegativity here is 4. Magnesium is a group 2 element, right? Now, the difference in the electronegativity here is 2. Now, in this case, what can you say? Of course, carbon will be electronegative, but if you look at the difference in the electronegativity here is 2. Why the difference here is what? 3. It means that in this case, even when carbon is electronegative here, the electronegativity is not as much as that of the copper lithium, that of the carbon lithium bond. So we can say that this bond here, or this carbon bond, the carbon atom here, is more electronegative as compared to the carbon atom in carbon and magnesium bond. Hence, the organolithium reagents are more used in synthesizing compounds when you are talking about organometallic chemistry, and I've explained the reason why that is. We said because it is more electronegative as compared to that of the carbon and magnesium bond. The organocuprate reagent, we are not going to dive or talk much on that, on the organocuprate reagent. So the next question is, how are organometallic compounds prepared? Preparation of organometallic compounds. Now, their preparation is very easy. You react the corresponding alkyl halide with the magnesium. What we are talking about here generally is Grignard reagent, which are the organomagnesium reagent. So alkyl halide with magnesium in the presence of ether, reflux it with ether. Are you getting it? Reflux with ether, and then the product of the reaction will be ROMGX, which is the organometallic reagent, which is called the Grignard reagent. It's a very simple synthetic tool. Are you getting it? ROMGX like that. Then the MG comes here and just form just more like an addition reaction. Now, this reaction, when you are carrying out this reaction, everywhere must be dried, and that is why we use volatile ether. If you use water, it will give a different product entirely. Are you getting? If a little water is present in this reaction, it will mess up the whole process, and the organometallic reagent will never be formed. Okay, so you must make sure that the place is dried, and that is the reason why most time the kind of ether that is used is dry ethyl ether. Are you getting it? Most time the reagent that is used is what? Dry ethyl ether, because any small water there will make the organometallic compound reagent not to be formed. The Grignard reagent will not be formed, and hence the product will not be formed because there is a little water there. So this reaction, you must try as much as possible to avoid water by all means. That is why the choice of dry diethyl ether is what? Very useful. Dry diethyl ether is very useful. So that is how the organometallic compounds are prepared, or the organometallic reagents are prepared. Now the next thing is the chemical properties of the Grignard reagent. We've talked about the Grignard reagent as possessing a carbon and magnesium bond. Okay, what are the chemical properties of the Grignard reagent? Now, the first property we have here is this. It says the carbon magnesium bond in Grignard reagent is covalent but highly polar. It's a covalent bond, but it's very polar. I've explained that. Why is it polar? Because the carbon is more electronegative than magnesium. Hence, this carbon is partially negative and this magnesium becomes partially positive. That gives the polarity. Are you getting it? That gives the polarity. So it means that the carbon will draw more of the electrons to itself, leaving the magnesium to be partially positive and then the carbon to be partially negative. And we know why that is, because they have different electronegativity. Carbon is more electronegative than magnesium and vice versa. Okay, the next one is the carbon atom is more electronegative than magnesium atom. I've stated that just now. And then the electrons in carbon-magnesium bond are drawn towards the more electronegative carbon. As a result, the carbon becomes partially negative and the magnesium becomes partially positive. I've also said that. Now, the next thing, I've also said this. We are just trying to give an overview of everything I've said before now. The alkyl groups in Grignard reagents, being electron-rich, can act as a carbanion or as a nucleophile. Now, I've explained that before, that the reason why these reagents are used as in preparation of alcohol from, let's say, aldehyde and other synthetic another compound is because that carbon here is partially negative. And because the carbon is partially negative, the carbon can be used as a synthetic tool or as a nucleophile that attack the carbonyl carbon of either an aldehyde or a ketone to form a product. Okay, now we are going to look at that as we talk about the reactions of organometallic compounds. Now, talking about the reactions, Grignard reagents now. Reactions with alkyl halide. The reactions with alkyl halide. Now, Grignard reagent reacts with saturated alkyl halide to form alkanes and alkenes. Now, let us look at the reactions and then see. If you have something like H3C, this is methyl, magnesium iodide. Now, if you react it with, let's say, something like CH3, CH2, and then Br. Now, according to the reaction, the product that will be formed is in such a way that this bromine here will break. Now, if this bromine break, this one also will break. Are you getting it? Now, if this one break, both of them will come together. And when they come together, the most important thing that will be formed is CH3 adding to this CH2, CH2. So you have something like CH3, CH2, which is this, plus this CH3 here, which will now form something like this. This other MgBrOI, they will become what? A byproduct. This is the most important thing, which is propane. So you see that it forms higher alkane, right? An alkyne. Now you can write this as something like this. In textbook, you see all the material, you see something like CH3, CH3. Note that this part here is telling us that there is a carbon here, right? Which is the CH2 carbon, okay? Now, in the same vein, you can also react it with an alkene. For instance, you have H3C, MgI. You can react it with an alkene, H2C, double bond, CH, and then CH2Br. Now, when we react it with this, what do you think the product will be? It will still be the same thing. What do? We break here down, and then break here down, right? And then the product of this reaction will be H2C, double bond, CH, CH2, and then what? CH3 plus the byproduct. Okay, now this is 1-butene, 1, 2, 3, 4, which is called 1-butene. This is what? Propane that is formed as a product. So you can see the Grignard reagent react with saturated alkyl halide to form higher alkanes and what? Alkenes. So this is one of the synthetic tools for the synthesis of alkanes and alkenes, okay? Because we said that the organometallic compounds, they have various use. They can be used to synthesize a wide varieties of products. Are we getting it? And hence the needs for them to be studied in organic chemistry. Now let's look at the next. The next says terminal alkynes react with Grignard reagent to form alkynyl magnesium halide, which on treatment with alkyl halide yields higher alkynes. So you have a terminal alkyne and you don't need a terminal alkyne. Now, what is the difference between a terminal alkyne and other alkynes? Now, the alkynes are known to have triple bond, right? Now, whenever you have an alkyne like this alkyne is called a terminal alkyne. Do you know why? Because the triple bond is at the carbon, the last carbon to the hydrogen. Are you hearing it? It's at the last carbon to the hydrogen. So in this case, you call it terminal because it's at the exterior. But in a situation where you have something like this, CH3, C, triple bond C, and CH3, this alkyne is not a terminal alkyne. Now, there are some reactions there are some things you want to manufacture or you want to make, and some reactions you want to carry out. And you don't need a terminal alkyne. You need an alkyne in which the triple bond is not at the end or at the terminal position. What do? Instead of looking for that one, you can actually synthesize it yourself by reacting what? By reacting Grignard reagent. Are you getting it? With the terminal alkyne, it will form the one that you need. Okay, so let's react it with the terminal alkyne and see what it will give. So we have the same thing, methyl magnesium iodide. A terminal alkyne, example of a terminal alkyne is H3C, then we have C, triple bond C, and hydrogen. This is a terminal alkyne, as I've explained before, and you know why. CH3 MgI. Now, when this reaction occurs, it doesn't occur like the one with alkyl halide, where the halogens of the alkyl will be broken off. In this case, this is hydrogen here. It's not easily broken up. Are you getting it now? So what will happen is that the magnesium iodide will actually attach with the at the position of the hydrogen, right? And when it attacks at the position of the hydrogen, what do you think we are going to form? This O group here. What I'm saying is this O group breaks down. This magnesium halide comes here. It removes this hydrogen from here and attacks here. This hydrogen now reacts with this CH3. Now, the product that you are going to form in this regard will be something like this. You are going to form H3C, C, triple bond, and then you are going to have C. Now, the MgI will attack here. That means the MgI will come here and come and stay here, right? So when it comes here, you have MgI. Are you getting it? Plus, then this hydrogen now will come and attack this CH3 here. So we have CH4. Because CH3 plus hydrogen will give a CH4. So this is called propyne 1, 2, 3 magnesium iodide. Propyne magnesium or propyne magnesium iodide. Okay, now what can you actually see from this propyne magnesium iodide? Can you see that it's just like another Grignard reagent entirely, but the only thing is that it's now longer. This is another Grignard reagent because this is a carbon metal bond. This is another Grignard reagent, carbon magnesium bond rather. Are you getting it? So you form another Grignard reagent. If you use this Grignard reagent now to react with an alkyl halide, according to what we said earlier, what is it going to form? It's going to form a terminal. It's going to form an alkene or alkane, but in this case now it's an alkyne, so it's going to form an alkyne. So we have MgI plus, let's say, an alkyl halide. Let's say iodide also. So according to the principle, what do we say? We say this one will break up. This CH3 will attack here. This one will break up and then form this product. So what we are going to have is a situation whereby this CH3 here is coming here and then the magnesium is bonding with this, leaving here. So the product of this reaction will be CH3, C triple bond C. We said the CH3 is coming there, right? So we have CH3. Are you getting it now? Plus Mg. Now this I plus I will give us what? I2. So you see that we've actually synthesized a non-terminal alkyne from a terminal alkyne by using Grignard reagents. Okay, so that is one method or one use of the Grignard reagent. This is a non-terminal alkyne. It's called 1,2,2-propyne or prop-2-ine. Okay, so that is that. Now this one is 1, 2, 3. No, this is 1, 2, 3, 4. But 2-ine. And this is what? Propyne normally. Okay, so that is for the reactions with alkynes. You should take note of this. Now the next one is reactions with aldehydes and ketone. Now Grignard reagents react with aldehyde and ketones to give alcohols. Now there are different types of aldehydes. We have the simplest aldehyde, which is formaldehyde, with the general formula of HC double bond O. Let me write it down. Simplest aldehyde is formaldehyde, double bond O and H. Now, if you react this with a Grignard reagent, let's say the same methyl magnesium bromide. Now, something will happen here. This bond, if it cleaves or it breaks down, if this bond breaks, you discover something that this will be negative, while this will be what? Positive. Is that not what we said? That whenever the bond breaks, the carbon will be partially negative and magnesium become positive. So when this negative charge act as a nucleophile, what do nucleophile do? They attack an electron deficient center. Are you getting it? Our electron rich center. So when this one comes here, this one will what? Go up here. Abi, or they attack an electron deficient center. The reason because this oxygen here is negatively charged and or is more electronegative than carbon. So this oxygen is pulling the electron cloud to itself, making this carbon here to be partially positive. So the negative from here will attack this position, and this one will have to pack up to form negative on top here. So the product of this reaction now will be something like this. The Grignard reagent, the CH3 is coming there. So we have H, we have O negative. Let me use a black pen to write so that we can use the red to illustrate the movement of arrows. So this gives us H. This becomes what? O negative. Now the Grignard reagent attacks the under here. So you have it as what? CH3. Are you getting it? And then you have what? Your hydrogen. Now recall that this is positively charged. Okay? MgB arrow. So the MgB arrow will come here positively charged. Now if this undergoes acid hydrolysis, if this undergoes acid hydrolysis, when we talk about acid hydrolysis, it means you are replacing everything here with what? H+, which is acid. And then this group here will no longer be here. Okay? If this undergoes acid hydrolysis with the elimination of whatever you have there, with the elimination of MgOHI or B arrow, what do you think will be formed? So acid hydrolysis, I said, means remove everything here, and then record that H2O will give what? H+ and what? OH- initially, right? Let the H+ comes here, it will remove this entire group from here. So we'll not be having any group here. So the product here will be H, C, and then OH will be attached here. Are you getting it? Because we said this MgBr will no longer be here because of the acid hydrolysis. And then you have CH3 and then H++. Now recall that we still have this MgB arrow that left. So you have it as Mg, then you have the B arrow, and then you recall that H+ entered here. So we are left with OH. So we have OH. This will be the product that will be left. So finally, the product of this reaction, let me just write the final product, would be something like this. Product of the reaction would be something like this. H, and here is what? C, OH, hydrogen, CH3 plus Mg, B arrow, OH. Now the question is, what kind of alcohol is this? Now you agree with me that this alcohol has just one alkyl group attached to the carbon carrying the OH. So that alcohol is a primary alcohol. So whenever Grignard reagents react with formaldehyde, the alcohols that are formed are what? Primary alcohol. So these may be objective questions. They may just answer. Whenever Grignard reagents react with formaldehyde, what is the product form? Or what we react with Grignard reagent to form a primary alcohol? The correct answer is formaldehyde. It's only formaldehyde that reacts with any of the Grignard reagents to form what? A primary alcohol. Okay? Now, other aldehyde react with Grignard reagent to form the secondary alcohol. Now, other aldehyde is such a way that formaldehyde is the one that does not have any alkyl group attached to it. It has just two hydrogens. So other alkyl group has at least one alkyl group attached to them. So if we react this with a Grignard reagent, right? According to the principle, what do you say we do? We cleave this. Here becomes negative. Here becomes what? Positive. So what happens? According to what we know, this negative charge attacks here. This one here pack up here. So the product of the reaction would be, you have CH3, CO negative. Are you getting it? Then here will be what? CH3, and then here will be our normal hydrogen. Recall that we said that this MgB arrow will automatically bond with this negative charge here to form MgB arrow positive. Then this group will undergo acid hydrolysis. This is not something we are supposed to be mentioning again and again. Now, if it undergo acid hydrolysis, what do you say? We say this group will leave and the OH will be formed on top of here. Okay? So this gives us CH3 and then COH, and then you have hydrogen and then CH3 plus MgBrOH. So this one will always be a byproduct of the reaction. Are you getting it now? Now, what kind of alcohol is this? It's a secondary alcohol. Why do you say it's a secondary alcohol? Because it has two alkyl groups attached to the carbon carrying the OH, which is the alcohol functional group. Okay? So that is the product of this reaction. So I can erase this to say that whenever other aldehydes react with Grignard reagents, the product form is a secondary alcohol. Now, how about if a ketone reacts with Grignard reagent? What do you think will be formed? A ketone has CH3 and then C double bond O CH3. Still the same approach. Now, the Grignard reagent may not necessarily be just CH3. It can be anything. It can be CH2, CH2, CH. It can even be long. It can have a double bond, whichever way you want to go about it. But at least it should have an alkyl group. That's what we are saying. And an alkyl magnesium bond. Okay? So this is CH3. I'm just using the simplest one to explain. MgBr. This positively charged. This negatively charged. Now, according to, we say when this thing cleave, it gives up negative and positive, Abi. Now, according to what we know, this negative is a nucleophile. So it will come, attacks here. As it's attacking here, this one will pack up here. So the product will be, you are going to form CH3, CO negative, CH3, CH3. Are you getting it now? Then this one now will become MgBr positive. Undergoes what? Acid hydrolysis. Right? So this gives us, when you talk about hydrolysis, meaning you are using water to break something down. That's the meaning of water, hydrolysis. So when it's an acid that is used, you say it's acid hydrolysis. Are you getting it? To break this complex down. Is that understood? So when you break this down, hydrogen attaches here. So this gives us C, OH, here is CH3, here is CH3, plus of course the product, which is the byproduct, MgBrOH. Now the question is, what kind of alcohol is this? This one has 3 alkyl group attached to the carbon carrying the OH group. So you call it a tertiary alcohol. Are you getting it now? So you see how this Grignard reagent is. Whenever the Grignard reagent reacts with formaldehyde, it forms a primary alcohol. If it reacts with other aldehyde, it forms secondary alcohol. However, if it reacts with ketones, these ketones, not ketones. However, if it reacts with ketones, it forms a secondary alcohol. Or let me say it forms not secondary, it forms a tertiary alcohol when it reacts with ketone. Okay? So that is for reactions with aldehydes and ketones. Now the next one is reactions with ester. Now, they react with formic esters and other esters to form secondary and tertiary alcohol respectively. Let's go. React with formic esters and other esters to form secondary and tertiary alcohol respectively. Now, the procedure here is quite tasking, but let's go through it together. If this is an ester, right? We are trying to just give a name. Let's say this is an ester. Of course, we know this is an ester. Then you have C2H5. If you react this with a Grignard reagent, CH3MgI. Now, what do you think will be formed? This is negative. Of course, we know this will be negative, and this will be what? Positive. If the bond breaks, then what happened? This negative charge here is a nucleophile. It will attack here, right? and when it attacks here, what happens? This one will come up here. Is that not so? Then when this comes up, it's going to form this product, which is R C O negative, and then this CH3 will be under here, and then you have OC2H5. Okay, recall that you still have the MgI, right? So the MgI will come up here. Okay, now when this MgI comes out up here, now there is something that can be done. How about if this group here kicks in here to form a double bond? I mean, this group here kicks in here to form a double bond. This group will no longer be here. Okay, if it's no longer here, as this one is kicking in, this one is also what? Kicking out. Okay, so we are going to form, first of all, a ketone, or maybe an aldehyde. So this is, we said this group is labile, it can kick out. As this one is kicking in, also this one goes with it. So we are going to form arrow C, here's what? CH3, and then double bond. Okay, plus, recall that this O group here followed. So we have MgI bracket OC2H5. All of them broke out. Are you hearing this now? OC2H5. Recall that this one is positive. This is what? When this one breaks out, it becomes negative. So both of them join together to form this product. So first of all, it will form a ketone. Now, when this ketone reacts with another molecule of Grignard reagents, it's going to form the desired product. So you see that in converting from esters to alcohols, you need at least 2 molecules of what? Grignard reagents. Of course, to every solution you serve, there are so many molecules present, so the reaction can take place just like that. So you have R, this C, double bond O, this CH3, which is the ketone that is formed. If you react it with another Grignard reagent, okay, let's say MgI, using GI for these reactions, this breaks, this is negative, this is positive. This negative can attack here, right? As it's attacking here, to now follow the normal reaction for ketones. This will give us R C, here is O negative, here is CH3, here is CH3, and then here is what? MgI positive. Now this can undergo acid hydrolysis. When it undergoes acid hydrolysis, now what do you think will be the product? To form OH, and then you have CH3, and then CH3. So this will form tertiary alcohol because it has how many OH alkyl group attached to the carbocation OH? That's 3 alkyl group attached. So you see that for this case, you need at least 2 molecules of the Grignard reagents to react with an ester. First of all, forming ketone. Then from the ketone, you can now form your desired alcohol. Is that understood? So that is everything that we need to know on Grignard reagent for now. And this lecture was meant to be for organometallic compounds, but we ended up talking about only the Grignard reagents. Are we getting it now? So the Grignard reagents, they are synthesized by a man called Victor Grignard, of which he received the Nobel Prize for his enormous contribution to chemistry, because the Grignard reagents, they are good synthetic tools for synthesizing alcohols and other compounds, particularly alcohols, various classes of alcohol. Now you can see that the Grignard reagents, if you want to actually get a primary alcohol, all you need to do is react the Grignard reagents with formaldehyde, right? If you want to get a secondary alcohol, react the Grignard reagents with what is it called? With other aldehyde. Then if you want to get a tertiary alcohol, react the Grignard reagent with a ketone. So basically, this is where we are going to end the lecture on organometallic compound. Thank you for your time. Make sure you subscribe to this channel, turn on the notification button so that you'll be notified whenever we post a new video. And also make sure you share, like it, and share. Thank you for your time. Give a positive review under comments. Maybe thank you to go a long way. Bye bye.